Hello everyone, welcome back to Dragonfly Engineering. So this week we're going to be setting up Big Yellow. This is the KUKA industrial robot, a 6-axis robot, to drill all the mounting holes into the table surface for our other robot workstation. This is the 4-foot by 3-foot aluminum and steel table that 2 other smaller robots are going to work on in the future. We're not actually going to get to drilling today, but I will show you the setup of the robot as far as teaching it what tool it has and its end effector, as well as teaching it where the plane of the table is as I just set it basically on the floor. And then a little bit of fussing with the controller itself. I actually bought this robot on eBay and the previous owner had like an auxiliary control box. And there were some issues with one of the components, so I basically pulled the bits and pieces out of the box that I wanted, and we're going to make a new little control box and then tell the controller to ignore the thing that was broken or screwed up in the other one. So we're going to go backwards in time in this video a bit. We're going to start with teaching the robot and end with what I started with, which was gutting the old control box. So I hope you enjoy, and let's start. All right, so we got the KUKA robot controller looking at the back-off input-output module that it's expecting to see to say that there's no errors in the system. And that looks to have worked out, because when I boot up the robot now and it sees what it's looking for, it is happy and it has 0 errors. So now we can run the yellow robot in fully automatic mode, which is nice. And that's what we're going to do to drill the holes in our table here. A couple of things that you need to do though after you start up a new industrial robot, you know, when you've got your configuration right with the electronics and you've mounted it to the floor and you've got your work table, is that you need to train the robot where this table is located, or this work surface. And also you need to train the robot what kind of tool it has in the end of its end effector, which is basically the end of the robot where it does work with tools or grippers or paintbrush, or in our case a Sharpie marker. So the first thing that we need to do is train this robot on where the tip of the Sharpie marker is, which is our tool that we're going to use to effectively draw out the drill points that we're going to confirm on the tabletop before we actually load a drill into the drill. We need to get into a configuration called tool tip training. So what effectively happens is that you guide the tip of the tool to a known point in space. The point in space can be anywhere, it just can't change. And then the robot actually, with the end of the Sharpie marker, is going to touch the point of the Sharpie onto the little tip of this copper wire that I was using in the EDM machine for drilling. And it's going to touch it from 4 different directions, and that will be enough information for the robot to figure out exactly how long and where the tool tip is for the robot itself. So here is our Sharpie marker, and what we're going to do is bring the tip of the marker down to our little point here to train the tool tip. So they say to basically just change the angle to 4 different orientations. So we'll try our first angle. So the default tool center of the robot, when you first get it, is the center of the flange of the robot itself. So excluding anything you bolt onto the end of it. So all these rotations are rotating around the center point of the flange of the robot, which is about 1 foot away from the actual end of our Sharpie that we're lining up onto this point in space. And it's more precise than you would think. I guess we'll find out how precise it is if it tells me that I was successful in defining the tip of the tool or not. All right, so that is our first orientation. And I am going to tell the controller to calibrate. Apply current position, yes. Okay, now it's telling me to basically change the the direction of the marker, but have the tip of the marker felt touch the same point of the wire that we just calibrated this first orientation. So I'm going to move up in Z, and then we'll change the angle of our tool. I'll zoom out for this. Okay, and then we're going to do this 3 more times to define our point. So I'll keep playing with the angle here. So I'm adjusting the 3 angles and the 3 world coordinate system locations in X, Y, and Z, and A, B, and C. All right, so now what I'm doing is I'm telling the robot how much this Sharpie weighs, the mass of it, because it has to basically account for really heavy tools and how it handles controlling its arm. It'll actually compensate for flex of the stages and the length of the arm and everything like that. But in our case, it's a Sharpie marker, so I'm just telling it it's 0.1 kilograms. And it's asking a bunch of other little questions like orientation, but we don't really care because it's just a circular tool. So we will say next. All right, so now we have a tool called Sharpie. Okay, so now what we can do is I will change on this controller to the definition of the Sharpie tool, which I think it probably defaulted as. So yeah, it's got tool 1 is loaded now instead of T0. And if we change our motion coordinate system to tool, well, currently the motion coordinate system is world. So it's considering basically the default X, Y, Z axes that the robot shipped with. It is what it calls world. You can also have the robot move relative to the tip of the tool. So you could say move robot around, but the tip of the tool doesn't change its location. Or you can change the robot around based on the X, Y, Z axis of the tool now. So what we're going to do is tell it that the new world coordinate system, or the new coordinate system is now the tool, which can be pretty interesting. And because now what we can do is with changing the angle, A, B, and C, the tip of the tool shouldn't move, but the robot will rotate its whole body around to keep the tip of the Sharpie marker exactly in the same spot. So let's see if that happens. So there we go. So now the robot is calculating to not actually move the tip of the Sharpie marker at all. And it'll spin its whole body around, keeping the tip of that marker exactly in the right spot in space, which is always kind of fun to play with. So if we play around with a different axis, axis B, then I guess that was the one I was just messing with. So we can try axis C now, and the robot will spin its whole body around to keep the point of that marker exactly in the same spot in the room. To the extent that the robot can move its body around inside of this room. That marker tip will not move, which is kind of fun to do. And it can be pretty useful for some applications. The only thing that'll stop it is if an axis goes to a limit. For instance, axis 5, its wrist basically starts to want to crash into itself, then it'll stop. But then, any orientation. So we can essentially travel in a complete sphere around the tip of that marker, and it just won't change location, which is kind of fun. I'll do axis A. But I do have to make sure that nothing crashes. And we can spin all the way around the other side. And this is a nice check to confirm that your tool height is defined correctly with your robot, is if basically you don't see any movement on the tip of the Sharpie marker. Yay. but I don't want to crash into the tabletop that I just spent all that time making. Anyway, so that is tooltip calibration. And it may have moved within like 1 square millimeter. Again, because I'm using a Sharpie marker tip instead of a precision needle point and another precision needle point, but that's pretty good for a machine that can reach, you know, 4 meters. Or not 4 meters, about 3 meters. Okay, well, enough playing. So the next thing we need to do is define the table surface and space relative to the base of the robot. And to do that, it'll be we define a base coordinate system. Instead of a world coordinate system or a tool coordinate system, what we're gonna do is define, using the tool that we just taught the robot with, where the 4 corners of this table are, or 3 corners. It only needs 3 corners, and then it can calculate the plane of workspace. And then we can move the Sharpie marker anywhere in our coordinate system that we define as this tabletop, and it should hit the numbers exactly right. Then we will do a base calibration. So let's see here, it's under startup calibration. We just did a tool, and now we're going to do a base calibration and a 3-point base calibration. And we will call base system number 1, and its name will be table. So now we will move our robot tip. Oh, actually, it's still moving in tool coordinate system. So let me switch out to world coordinate system, and then we can move Z up. And then we'll reorient our marker so that it's a little more practical for touching off the corners of this table. Okay, we can move our point out of here. Now I'm going to come to this corner, and I think the first point you teach is considered the origin, or the 0 point of the table. So we will bring the pen down to the table surface, or close to it. Now when I switch this Sharpie pen out for a drill bit, I'm going to have to either offset the position in the toolpath program, or I'm going to have to reteach the tool height with the actual drill bit that I'm going to use, using that 4-point method again. So what I'm doing is I'm just bringing the marker up to the corner of the table, and then, similar to the previous exercise, I am going to find, as close as possible with this Sharpie marker, the corner of our cast aluminum table here. And again, I'm holding on to the panic bar on the back of this controller. So if this robot starts to take off on me, I will subconsciously panic and clinch up, and then break the effectively hit the equivalent of an emergency stop. So the robot will stop immediately if I activate the panic bar. Okay, now I'm bringing the tip of the Sharpie down to the exact corner of our table. Now once I find this coordinate system, I can't move this table, but I probably will put some weight on it to help stabilize it for drilling if it's needed. Okay, so it says move TCP to the origin of the new base coordinate system, and I'll hit calibrate. Apply current position, yes. Okay, now it says move the TCP to a point on the positive x-axis of the new base coordinate system. So positive x will be towards the camera, or towards you guys. So we'll go up in Z, because we're still actually moving in the world coordinate system, because the robot doesn't yet know the plane of this table. And then we'll move in, in X. Okay, so we'll keep moving on X. I'm going to move over there to eyeball basically just the edge. We only really care about the edge not the XYZ location, but just the Y location of this line. Now, I do have to get the Z correct because we need 3 points to define a plane, because we don't want a planar walk-off on our drill pattern if I get the Z height wrong. So it's just easier to set all Y and Z here. Okay. All right, I'm gonna hit calibrate, apply current position, yes. Okay, now it's asking for the positive Y location, so we're gonna repeat the same process. Move up in Z, and then we'll go over in Y. So you could say it's kind of similar to setting up a mill. There's just a little bit more to it because there's 3 angles as well. But, you know, I guess it's the same as setting up a 6-axis mill or a 5-axis mill. And the farther we can stretch out, the more accurate our plane is going to be. So now I'm going to come down in Z and move X so that we can define where Y is. Okay, right there. Then I will hit calibrate. And yes. Okay, so now we have a tool 1 and a base 1. So we just defined our base 1. And what I can do now is switch the jog mode on the controller from world coordinate system to base. And base 1 is selected, so now I can move up in Z. I'm going to be careful with this since it's a new definition. And Y. And the pen should just follow right along the edge. And then we'll come down in Z. On this controller, it will actually show you the X, Y, Z, and ABC numbers. The robot is telling me that X is 0.61 millimeters, Y is 33.68, and Z is 29.5 millimeters. So if I move manually, I'm bringing the pin down to the final location where X and Y is basically right on 0, and Z we're 1.25 millimeters above the surface. So I'm going to bring Z down. Here we're at 0.52 millimeters. 0.3 and 0.07 millimeters. So let's see how it's looking. So it's looking good. Yeah, it's basically right there on the money. I can't visually see any offset. Keep in mind it's a Sharpie marker. So I have had the cap off of this marker for a little bit. So let's see if there's any ink left in it. So we'll go Z plus. Again, we're in the tabletop work coordinate system, and we're using the tool offset that we programmed. So we'll do Z plus, and we'll move Y positive, X positive, then we'll come down on Z. So we're about 100 millimeters in X and 150 millimeters on Y. And Z we can come down, probably do minus ½ millimeter to engage the marker tip. So right there we are minus 0.4, and then we can draw. And if our marker survives, then that tells us that our table calibration is correct. Oh, it's starting to bounce a little bit there. Or maybe I've just cleared out the dried ink. So now I'm going back over and it's drawing a nice shape again. Of course, it's deviating a little bit. I think the felt of the marker changed a little bit. Let's try Y minus, and then Y plus. So that's looking good. So I can use this to draw out my my cut lines in future sheet metal projects, or just put the plasma cutter right onto the end of this robot and start cutting. So there we go. We are in business. So the next step is going to be to, oh, can you see me? Yeah. The next step, we're going to replace our Sharpie marker with a drill and basically drill the breadboard pattern or the reference mounting pattern grid in this table so that I can get it in the clean room and load some smaller robots onto the surface of this table and have it start working. So the grid pattern will be pilot holes that we can thread with an M6 screw, probably every 50 millimeters. So we're gonna spend a while just drilling with this robot and a drill bit in here to finally finish out this table so I can get it working in the clean room. In some of my previous episodes, when I showed the insides of the smaller robot, the benchtop robots, I talked about a Beckhoff EtherCAT module that is an input and an output device, and that's what this guy is right here. So the Ethernet for the robot controller, which it uses something called EtherCAT, which is a communication protocol similar to, well, it's basically Ethernet for networks. It uses Ethernet to talk to the different components inside of a electronic assembly. In our case, this is the unit that we want to keep, and this is basically identical to the ones that are in the smaller robots. And then one of the modules that was bad are one of these expansion devices. And I could tell that one of these was bad because the configuration software for KUKA said that whatever this number is, the EL1809, one of those was not responding. But I don't know which one it is. And these modules, so this is one module, and these all fit on what's called a DIN rail, which is this metal rail right here. You can see this junction is still attached. But these expansion modules fit onto the end of the Beckhoff. Let me get it oriented. And you can see that there's these gold connections here. These are like leaf spring connections. And then over on the expansion module, there's little gold contacts. And these all stack up to each other and create what's called a bus connection in the back, where like all these gold contacts basically just daisy chain along, and then these all stack together. 4 months ago, started taking all this apart, and I took this DIN rail off to kind of assess the situation. So what we're gonna do is we're gonna pull this module out of this electronics cabinet, and we're going to use this thing. Again, this is a DIN rail mount. And for those who aren't familiar, a lot of control cabinets are DIN rail mountable devices that all fit on these rails. And then these are wire guides. And usually a plastic cap can clip onto this to create like a tunnel of wires that can then poke through the side walls and things. But back to the point. This is a power supply because this Beckhoff device runs off of 24 volts. And this is a 120 to 240 volt AC to 24 volt DC converter, or a power supply. So we're gonna keep this thing, and it's already, since I started gutting this system, it is hooked up to basically the 120 volts AC in with these circuit breakers, which are also DIN mount. And I think that's all we're all gonna need for now. There's other interesting things in here. There's like a big, switch here, which connects to the door mechanism there. So this cabinet is maybe useful, but it's just way too big for what I need. Other things of interest in here is this Keyence barcode reader, which is kind of cool. I think this is like a couple of $1,000, but this goes on the robot. And then there's a corresponding module somewhere in here that receives this signal. There's also a little motor controller here, which is cool. So I could probably use that in the future. And then these are the bad modules I was talking about. So let's go ahead and pull this unit off. And you can see that whoever had this before did a lot of the wiring, which is nice. So I think I'm gonna actually pull this DIN rail off, which has this breakout here for all these connectors. And I can reuse this. I'll probably just put this chunk, these wires, this guy and this guy in an individual smaller box that will sit on top of the robot controller. So these little connectors here look like this. This is an individual one, and they can pop into the DIN rail. There's a way to do it. You basically snap it in like that. And then if you want to pull a wire out, then usually you shove a screwdriver in there and it releases a little spring-loaded mechanism to pull a wire out. So we're going to pull all these wires out, which have uses that are no longer in my need. So we shove the screwdriver into that hole, and a little spring-loaded clip pulled back, and now we can pull the wire out. So this DIN rail stuff can be convenient. It can also be very frustrating because sometimes it's not obvious how to remove one of these things once it's snapped in. There's probably a screw head underneath this bank of parts, and whoever designed this box hid the screws, which kind of sucks because I may have to take some of these out until I find the screw head to remove this rail off of this cabinet. So here is the top screw right there. So let's unscrew that guy. And I got it in there. I have to get the well, I guess I need to get the socket wrench. Okay, we got the socket wrench. Let's see if this does it. Man, they really cranked that on there. There we go. All right. Okay, looks like it's anchored somewhere here in the middle. I guess I need to pull a lot of this stuff out of there just so I could take the DIN rail off. All right, so these are the guts that we pulled out of the supplemental control box from the last owner of the big yellow robot. So it's best to have this thing mounted the way it was intended with a DIN rail. And since this needs mounted, I might as well go ahead and mount the DC power supply as well as the circuit breaker. And I basically just pulled these guts out of the old box. So we're gonna make our own control box. And then all of the outputs and input wires for the Beckhoff controller, all of these things with their own DIN rail terminals, some of which are still connected, we are gonna mount on a second DIN rail in this little box. It's gonna be a little tight in here, but I figured since we're doing it, we might as well do both. So I'm gonna mark and cut this stock DIN rail that I pulled out of the that huge control box into appropriate size, and then we're gonna mount the DIN rail down and then mount our components to the DIN rail. And then hook this up to the KUKA, and it hopefully will have all of its errors cleared so we can run the drilling program in automatic mode. So I will mark and cut these and be right back. All right, so this is a step drill, and it's good for cutting holes in sheet metal because it cuts from the side instead of the tip. So there's not nearly the big breakthrough burr that you get from a twist drill. This thing kind of just shaves off from the inside of the hole and makes really nice holes. And you got all your sizes in one basically triangular bit here. 2 flute, and we'll stick our stock in, and we are going to drill the hole for our electrical service grommet. And this is not a critical location or anything. I don't want to drill into my table though. I think this is aluminum. All right, well, we got the position of it, and that may be the right diameter. But I don't want to drill into my table, so I'm going to finish this off with a hand drill. So, as you can see, the backside of the step drill hole does have a burr on it, but these step drills have a chamfering feature in it as well, so you can clean up your hole that you just drilled. So I'll stick this in the hand drill, and I'll come back on this side and clean up the edge, and we'll see if we can fit our grommet through that hole. Whoop. These should be hard to insert so that they're hard to pull out in normal use. It's kind of like O-rings in a cylinder. You kind of have to collapse the grommet on itself and then get the molded flange through the hole. This hole may still be too small in diameter. Let's see if I can get it. There we go. And then you kind of massage the rubber to get back to a good shape. So there we go. Oh, you know what? I think I need to populate the den rail before I screw it in. Otherwise, I can't slide the components on the end. Go from the backside. Sometimes these have like a little release feature, all the orange plastic stuff. Give it a wiggle. There we go. Okay, so our Beckhoff module is mounted on the den rail. Next will be the power supply. You may want me to pull the orange thing back. If I worked with this stuff every day, it'd probably be a lot more smooth. But I do not use this stuff every day. There we go. It doesn't want to. There we go. It is a little tight. They must make this stuff with tight clearances. There we go. And then to release this, you pull the orange part, and then it'll flip out like that. I guess I should have done that to start with. Oh well. I see this has an orange. The Beckhoff module has a little orange thingy as well. Oh, there we go. Just push that down and it quasi-clipped in. Let's go back with our power supply. Okay, so that locked in place. And then finally we will do our circuit breaker. And this has a channel lock as well, which is black plastic, which you just push down. The other one's missing, but I think that's all right. Okay. And just like that, we've populated our den rail. Finally, I'll put this, just let all those drape down. I'll put this ground contactor on. Now these actually need to have a good electrical contact. So there's a screw that you actually bite into the metal of the DIN rail so that you get a good ground, a chassis ground. You can hear how it's wanting to bite in there. I do have one screw that has longer teeth. I'm gonna have to grind it off after I screw this guy in. Okay, yeah, that's touching. All right, so now we will populate all of our signal DINs or contactors, DIN mountable contactors. Okay, there we go. Here's all of our contacts. So now when I want to connect something, I just stick the wire in here with releasing the little spring-loaded clip inside of that hole down there. Yeah, in this hole, there's all the little clip, or the little spring-loaded wire clamps, and you can shove your output wire, probably to like a banana plug that I'm gonna have on the front of this thing. So, but for now, this should do it. And we'll just tidy up a little bit in here. We're gonna drill a hole so our EtherCAT plug will fit through the back. Yeah, that should be all right. You can start a hole with these step drills as well. It's not quite as good as a twist drill, but it works. See if that's enough. Yeah, that'll work. So I'm gonna have to find a grommet for this size hole. I don't know if I have one, so I may have to come back to that. There's also little two-part clamp things that you can get. Let me clean up the backside. Here, I'll show you how to clean up the backside with a step drill. This is probably aluminum, this sheet metal housing. And I got to vacuum out all the chips, unlike the plastic shredder that I just bought. Okay, whoop. Okay, so we'll stick this drill in, and then I can just clean up the inside of the sheet metal with the chamfer edge on this step of the drill. And the rest will just kind of wipe off. Might have to flick a little bit off. Anyway, so we got a nice D-bird hole in our sheet metal, which is a real pain with a twist drill. All right, so our EtherCAT will go in. Let me just dump all this out, actually. I'll blow this out too. Alrighty, so EtherCAT plug comes in, or Ethernet cable comes in and plugs into our EtherCAT I/O module, the Beckhoff I/O module. And I can slide it to read it. In and out. Okay, so the top plug is the input. Okay, Ethernet goes into the labeled input Ethernet port on the Beckhoff controller. And then this cable will allow communication between the KUKA robot Ethernet system and this controller. Of course, this little rubber thing is getting in the way. There we go, it snapped. There we go. Okay, so we're over at the KUKA controller, and this Ethernet cable has been plugged into the communication port. It's labeled below the controller. And let's plug this Beckhoff module in. This is just a regular house power. And you can see our little green power light is on here, and we've got the 2 green power lights on the Beckhoff control module. So the next step will be to turn on the KUKA robot controller, which I'm doing a little bit off screen. And we will see if we start to see Ethernet activity. You see, it may be hard to see down there, but at the base of the green plug, or at the base of the blue plug, there's that green light, which shows that there's at least something happening with the Ethernet. And as the robot boots up, we should start to see traffic, like little flashing lights on that Ethernet connection. And I see some. So you can see here that we got some flashing lights. So at least the Beckhoff is talking to the robot controller to a certain degree. Focus in on that. So that's good to see. Well, that'll be a wrap for this week. Thanks for watching. And if you'd like to see more, then please consider subscribing and hit the icon or the little bell icon as well, so it'll remind you of new episodes. And for next week, we are going to actually drill the table, and my wife April is going to help program or convert the G code from the toolpath program into actual KUKA code that this robot can understand, and it's going to drill probably 600 holes in this table. So stay tuned to next week, and we will see you then. Thanks. Bye.